In the second measure, the plan is very simple. I will state a slightly more precise statement for this case 4, and then we will see the proof, whatever it is, and then we can. Okay, so let's start. So we start with family of Whitney balls. With respect to origin in R plus R. So now let's move to one dimension to have things more simple. And we want that if we take Bj, then the diameter of Bj is 2 to j. So just to connect j to something that makes sense. Then for each j, we take an adaptive multiplier. Then we define lowercase m to be the sum of these multipliers. And then we define a pair of edge functions dividing the over. And of course, now I did the notation twice, so this is of course just the binary multiplier coming from n. Okay, so these are the objects. Okay, and then I say that for a triple of exponents, we have constants such that for pair of test functions. We have the bound we already have. Okay, maybe things are a bit in the wrong order, but anyway, you should be getting the idea. And then let's draw a picture, remind you. So our singular point is origin. And then we take these, we divide the balls, one for each diameter. And the multiplier is just summing these things up. And this is the interesting case of Koifman-Meyer multiplier. And in what follows, I will be interchangeably calling this a para. That's another word. And then people ask, why is it called para product? And the reason is why it is because everyone else does the same. But the point of the word para product is that this operator is something that is bilinear, and if you differentiate it, it satisfies a product. So it has enough characteristics of a product to be somehow associated to the word product. So it's a para product. And in time frequency analysis, this para product, it's just a type of object for which we have these L2 counts. Yeah, so I once heard a conference talk where the speaker was trying to find what is the definition of para product, and I think his take from the literature was that it's bilinear, it satisfies Hölder's inequality, and it satisfies the product rule in some sense. So in their terminology, I'm proving that my multiplier is para product because I'm proving the last missing piece. Okay. And then the proof, as all the proofs, must start with some reductions. So first, without loss of generality, we assume that each of these nj's is of product form. This we can do. It's the same Fourier series argument as in the first case. So when we go to the definition of Tfj, we can do the trick inside the integral, and then we just pull out the Fourier series, and we are having a series of Koifman-Meyer multipliers, so that for each of them, the symbol is in the product form. So this we can do. Oh, and then this is not a reduction anymore, but the next step is that we can make a case. We assume that both functions vanish at origin. And now in the picture, this corresponds to the case that we are avoiding both axes. So we are somehow staying close to the diagonal. So when we project to down, we are far away from origin. When we project to the horizontal direction, we are still away from it. So this would translate to this thing happen. And now, if this were the case, then our theorem is simple because, okay, we can just do Hölder's inequality first in the sum, then in the integral. Maybe I can even write it here. So I take my t. Then I say that I do positive parts in the sum. This is the space right there, but this is still the same LR. And now I can do the Hölder's inequality to say that this is the square function of f times the square function of g. And now this was the special case of the median multiplier theorem that I mentioned, that the splittable Payne square function is bounded in here. So here I can say that I have constant times f and g. So this case, where we are avoiding both axes, is easy. It follows just by the Fourier series. This case is now done. Then we have case 2, where this is not happening. But in the case 2, we can still assume that we have one of the indices where n0 is always 0. And the way to do that is that we decompose the plane into several sectors. So we have, say, 2 forms. In one, we collect everyone who is touching or above the lines, and in the other one, we collect every ball who is below. So this is form 1, and this is form 2. And now we have 2 forms that we found separately. And now these cases are symmetric, so we may assume that this 0 are okay. And for NJ2, we don't know anything. Okay, now the picture is kind of clear why this will always happen, but the thing I have written in my notes, but I didn't say, is that you can deduce from the fact that you are Whitney ball that at least one projection doesn't contain zero. because if both projections contain zero, zero would be inside the ball, and that's not possible for weaving. So that's why at least one projection must exclude origin. And then we can just divide these balls in two families. In one of them, we can say this, in the other one, we can say the other case. Okay. But all in all, we can always assume this. Okay, and now we should do something for the troublemaker. So there is still this NJ eta who is going to pile up at origin. Maybe I should draw here something more to draw your attention to the disaster. So now this need not be zero. So we would like to force it to be zero by some way. So now we take the Littlewood Bailey decomposition, the standard one. I better use the standard notation. So let's take high J to be Littlewood Bailey, or this would be a function such that, sorry, it's a function that is adapted to B0 to J. Then we have phi J to be phi J minus phi J minus 1. And then we want to have the Arbitrium unity property. Like this. And now using this standard Littlewood Bailey decomposition, so we have these functions phi j living in the annuli, and phi is the one in the middle. So we can decompose this multiplier in two parts. So we take the thing, and then we just subtract the value at origin. Okay, now Blackboard is really bad.
Plus.
Sorry? So now we have decomposed this guy in two parts. In the first part, the value at eta equals 0 is 0 again. And for that kind of multiplier, the case 1 applies. And then we have the other part where we don't have this slightly mysterious mj, but we have phi, who we constructed by hand ourselves. It's the standard Littlewood Bailey piece, and a constant. But now this is just a constant, so we can include this one in mj1. So mj1 times mj2 0 is still having the same properties that the old mj1, because these multipliers are bound. So now we are left with several multipliers. So first, there is case 2 thing, case 1 thing. So here is one multiplier. Then for the second one, we decompose this further. So when we have this little wood baby thing who looks like this, we can say that it's 1 minus all these bigger ambuli. So 1 minus all these other ones is the same as the second one. So when we write here 1 minus the sum of size for k larger than j, we will get 2 more multipliers. So we will have and then the remaining one is mj1 psi times sum k goes on say j minus 3. Okay, there is some borderline between first so much. Where is it? And now this is the size. And the thing with the size is that they are, of course, perfect in the sense of color of signal theory, meaning that they are vanishing to the storage. Okay. I put there just lines, but maybe I should give them letters. So this is A. This is B. And this is C.
With psi k.
Yes, yes. Thank you. Okay, so now as it were, A is done by case 1. B is done as it is of 1. It remains to bound the part C. Okay, and now I might have forgotten the most of it. But this is really not essential because this goes as a package. And now this last thing is dealt with basically application of Binny's theorem and all the linear estimates we have. So we have the sum over j, and we have the sum over k. Then we have the multiplier M1 tilde J, and tilde means now that I have included this guy. Although I will get these errors. Then I have I and I do compute the LR norm, this guy. And now to compute the LR norm, we dualize. So we multiply by a function g, who is in the correct, sorry, h, who is in the correct LP space. Okay. And now this is the form we should integrate and get the bound. Now we have to look what happens. So here is already K is always something larger than J. So we will say that there is region like 2 to J here, in the vicinity of which the M1 is. Okay, there is the case when K is equal to J, but we ignore it for the time being. It's a simple additional argument, but let's assume K is much larger than J, because this is where the arguments happen. Then we have the support of psi in the annulus of radius 2 to K. And now we look at this product function. And we ask, where is the Fourier support of this one? So now the Fourier transform of product is the convolution of the Fourier transforms. And the support of the convolution is contained in the Minkowski sum of the supports of the ones to be convolved. And that's why if I take this large annulus of radius 2 to K and I Minkowski add the ball of radius 2 to J, I will get something that contains the important part of the support of H, because any part of H who is not in the sliding pattern annulus will go to 0 by Blanchet, because now I can see here an L2 inner product. So the part who is not here is orthogonal to this one, so it will go away. That's why for free, I can add here K plus L, and then I add here the sum where L goes from say minus n to n. Okay. So if the stuff is somewhere else, inner product with this guy will kill it. Okay. And then the remaining part is to just change first the order of summation. And I'm not going to write this thing because this formula is too long. But you first change the order of summation. This is the only factor who depends on J. So it's left alone with J sum. from minus infinity to k, roughly. And then I will put absolute value inside, and I will say that my first factor will be supremum over k of absolute value of sum j going from minus infinity to k, and then I have just this thing here. Okay. And then I'm left with absolute values of these things, but now both two are having this Fourier projection with vanishing moments. So I can apply the Littlewood famous square function to square some smaller things. So that's why by Hölder's inequality, I get here the square functions. And then, because we are integrating eventually, you still have to apply Hölder's inequality. Now you have all three functions in a nice form. The integral coming from this one is bounded by Littlewood inequality. The same goes for this one. And this last one is maximally truncated singular integral. Also, that kind of operator is found in the colors. And that's how you come to this one. Okay, so this is it. I left out this case where j and k are equal, but okay, that's an easy case. And then the last remark I want to make is that in the setting of uniform bounds, these multipliers that must be dealt with are different. So there, instead of having mj having this kind of isotropic estimate, so their differentiation to all directions works the same, those estimates will be anisotropic. So there will be an additional parameter, like where should I put it? Say here that this would be say plus n, and I would like to have uniformity in m. It's causing some additional trouble, but the main idea of the group is the same. So what it essentially makes that in the beginning one of the multipliers is longer and it must be decomposed further, but after this additional decomposition, the argument follows the same path. So there is the first case when everyone is avoiding the coordinate axis where you can project to any direction, and the claim follows from the Littlewood paving. Then there is the second reduction where you say that you can assume that one of the coordinates is always 0. And for the one who is not, you will do this kind of decomposition to one with 0 and one where the non-zeroness happens in a controlled way. And once you have non-zeroness happening in a controlled way, you can go do this telescoping. And the change from MJ2 to 5J, this was in order to have this algebraic miracle happen. Because with the sum of MJ2s, you don't really know that this would be 1 and this would be like this. But with these 5 subsides, it works better. And then the last part is that you will see the maximally truncated singular up here. Somehow there is always Hilbert's inequality in the scale parameter, which is now J or K, and there is Hilbert's inequality in the space parameter, which is the integration. And somehow you must always respect the Hilbert scaling, you know. Okay, I think I will still have 20 minutes today, but I think I'm done.
Any questions? Comments? Please? No.
So if I understand this proposition, it's a family of balls where for each radius you have only just one ball. So
Yes.
it's not like a full decomposition.
Yes.
Not the full decomposition.
Although,
of course.
although if you want to deal with the full decomposition, you can do this kind of pigeonholing to reduce it to finitely many multipliers to this form.
Oh, okay.
Somehow, first you decompose with respect to directions, and then inside each of the directions, you say that I just pick one ball from each of these ranges. And in each of the ranges, by the properties of the Whitney decomposition, there is dimensionally many of them. So you will exhaust the whole multiplier by dimensionally many things of this form.
Could you repeat why we can assume that our multiplier has product structure? Is reduction in
You need this without
this one, yes.
without loss of general. Okay, do you remember in the first lecture, I had this second item where I had a smooth multiplier. So maybe I wrote a picture so you will remember. So for each of these adaptive guys, I have the support. I will multiply it by the tensor cutoff, and I will expand a Fourier series here. And now because my thing is smooth, the Fourier series decays, and somehow I can pull the Fourier sum out from everything. And because I'm controlling the LP norm of this thing, I do Minkowski to pull the Fourier sum out of the LP. Okay, and these Fourier coefficients AK, you can have them decay very fast. And that's why somehow, yeah, it's not the same, but it follows.
The questions? So, okay, let's start here and then we finish for today. Tomorrow we'll resume at 9. That's all. Thank you.